Hello, welcome back. We are going to discuss, we continue our discussion. I think last time, if you recall, we were talking about the potential energy concept. We talked about the gravitational potential energy, we talked about spring potential energy, and we also did one of the examples of how to get the work done by friction. And in fact, we tried to show that the work done could be zero even by static friction. It could be positive, it could be negative. In some of these cases we saw the other day. And individual forces I took and then tried to explain. Of course, I go to that, but before that, there is another very fundamental equation which we call as work energy theorem. I told you the mechanical energy forms are potential, kinetic. I mean, honestly speaking, all potential energy cannot be converted to kinetic energy. People have a wrong impression because this is another wrong seed that I am going to plant in your mind if I say every time kinetic energy is converted to potential and potential to kinetic. It doesn't happen this way all the time. In fact, if you look at the natural systems like Earth atmosphere system as a whole, it receives energy from the sun. A huge amount of energy from the sun it receives. You get the point? Of which only a fraction, a small fraction is available for conversion. It is received, partly reflected, partly absorbed. Out of this absorbed energy, a very small fraction is available for conversion, that is stored as potential energy, of which a part is available for conversion to kinetic energy, that is called APE, and of this APE only a fraction is actually converted. This is the natural atmosphere system. If you read 100 units, if it is received, not even 0.01 is converted to kinetic energy. In fact, even less. And with this kind of kinetic energy, now you see such a havoc is being created with tsunamis, cyclones, depressions, troughs, monsoons, and the huge amount of turmoil. Anytime the whole globe is covered, half the time, rather half of the globe is covered with the clouds, so you can see the activity. So what we say here is in a very small teacup pot we talk about, we take an isolated system, and then we say this is potential and kinetic. We're going to look at that. We're going to look at that one by one. And so what is this kinetic energy? You know, I did not have to dwell at length about the kinetic energy. It is energy possessed by any moving body by virtue of its motion only. Right? So, in fact, work done on a body is manifested as kinetic, and I am writing in bold letters. The very important point you have to say, where you want to have, you have to have work done. But this work done could be stored as potential energy, possible. Sometimes the work done in the body is manifested as kinetic energy. I am trying to push the body, I did work, and the body is moving. And it got that energy from me. You see, the energy is continuous, that when it possesses that. But work done is not continuous, it is discontinuous. As long as you do that, you apply the force, and it keeps on doing the work afterwards for work. So the work done, what happens to the work done? The other day I spoke about the stories of potential energy. Now I am going to speak about the manifestation. Sometimes it is reflected, it is visible as kinetic energy. You get the point? So work done this way. And this is, of course, I need not have to go and prove this. It is half mv square. This is the kinetic energy of the body. Now, kinetic energy can vary, of course. Now, what is this work energy theorem? Well, you see, I said a part of it is stored as potential energy when you do work, provided it is done by the conservative forces. A part of it could be stored as manifested as kinetic energy. That is possible with any kind of work that you do by any force. So, in nature you have conservative, non-conservative, they all coexist together. The coexistence is a beautiful word. People don't understand the meaning of it, coexist. I remember Pandit Jawaharlal Nehru made a statement, the only alternative to coexistence is co-destruction. When he was talking about the neighbors, etc. And today, another anecdote you can create, you are bound to coexist with coronavirus. There is nothing else that you can do. Live with it, beware of it, be aware of it. Then I think things will be much better for you. Alright? So, coexistence. Now that is important. Okay. Now, conservative, non-conservative, all. Suppose I am taking conservative forces, non-conservative forces, external forces, and of course, these are all internal, external, everything. Conservative, non-conservative, external. All this is what I call as sigma f. Okay? When I take sigma f, in fact, if you wish, you could take even the pseudo forces as well. If you have pseudo forces, these are all total. The work done by all these forces on a body is equal to change in kinetic energy of the body. So wonderful theorem. People think it is a new theorem. No. It is same as second law of Newton. No difference whatsoever. I am going to show you what is sigma f. Mass into acceleration. And how do you write acceleration? Either dv by dt or m dv by dx. This is how we can write it. The total work done by internal conservative, non-conservative, external, pseudo, all is equal to sigma f dot dx integral. How do I get it? M v dv by dx. Now, m integral v dv mv square by 2. From some initial value to final value, so you have half mv square minus half mu square. This is the work done by all forces. This is final kinetic energy, this is initial kinetic energy. The change in this kinetic energy is what we are calling it as work done by all the forces. It's very, very, very interesting. And as I said, you can use this in all contexts. If you are using pseudo force, you can do. If you are using the only real forces, you can do. If you are using conservative, non-conservative, combination of conservative, non-conservative, combination of conservative, non-conservative, external, And a combination of all these with any combination you wish you took, it's a universal relation. Universal law, not a separate law. It's directly deducted from Newton's second law, therefore it is the most fundamental law in mechanics. And that's what we call as work-energy theorem. Now you see, if you have work done by internal conservative forces, work done by, now I'm taking an isolated system, if work done by internal conservative forces is always equal to what? Minus delta U. I have already shown you that. The potential energy change is negative of work done by internal conservative forces. So on minus side I kept it here. So minus of U to U is potential energy. So I can write it as U1 minus U2. 1 and 2 are symbolic. You may start at any time interval of your choice, end up at any time interval of your choice. It doesn't matter to you at all. So you have got U1 minus U2. Okay. Supposing I have only internal conservative forces and nothing else. Only the system is isolated, so no external forces, no non-conservative force, because I said it consists of only conservative forces. In which case, from work-energy theorem, this is nothing but delta K. That is K2 minus K1. Well, interesting. But what is WIC? U1 minus U2. What is this? K2 minus K. Now take 2 onto the other side, 1 onto this side. Wow. And this is nothing but the initial mechanical energy is equal to the final mechanical energy. In other words, in the scenario that we have envisaged here, the total mechanical energy of the system is conserved or it remains constant. What are those conditions? In an isolated system. The moment I take isolated, no exchange of matter, no exchange of energy. So no external forces involved, no external torques involved, nothing. So isolated consists of only internal conservative forces. Okay? In which case mechanical energy is conserved. So the statement is, in an isolated system where the system consists of only conservative forces, the total mechanical energy of the system remains constant. This is called the principle of conservation of mechanical energy. No, it's greatly, rather not slightly, greatly different from the so-called universal conservation of energy principle, where you say energy can neither be created nor destroyed, but can be converted from one form to the other, etc. Well, that is a very broader definition and broader conservative law, equally valid in every way in all systems. But this is a narrow. I am confining to a system. It's an isolated system, no external forces. Therefore, and not only the no external forces, internally, no non-conservative forces must be present. Or, even if they are present, they should not do any work. Understand the concept. I don't want to go with the bookish statement. Isolated, no external forces. System consists of only non-conservative forces. Or, even if it consists of non-conservative forces, and if they do not perform any work, also it is okay. In such a scenario, the total mechanical energy of the system remains constant. A thing that you have been using without making the statement P plus KE is constant. That's what we're saying. P plus KE is constant. That is the meaning of it. But you can't use it wherever you like. You have to be very, very careful in using this. Gravity, of course, you are using because there are no other complications there. Okay? Now, you see how we are going to deviate from this. If I have external forces and internal conservative forces, then this is equal to what? Change in kinetic energy. If you have external forces acting, that external may be conservative, non-conservative is immaterial. But I know what is WC. I know it is U1 minus U2. Alright? So WE is equal to, you bring it here, U2 plus KE2 minus U1 plus KE1. Wow, interesting, truly interesting. So what is the work done by the external forces on the system? Change in mechanical energy. Sometimes this may be only change in kinetic, only change in potential, or change in both. It makes no difference. What do you mean by this change in mechanical energy? Generally, this results in thermal energy conversion. Generally, most of the time. I dropped a body, it struck the ground, so there is an external force, ground has interacted with that, this kinetic energy has come to zero. What happened to all this energy? Is bound to be converted to thermal energy. That sound immediately, cascade impact, it could be converted to molecular thermal energy. Okay? So if you have external forces acting, that will result in change in mechanical energy. Alright? Now, I am now taking no isolated. So isolated means no external. Therefore, how many forces can you visualize? Internal conservative, internal non-conservative, both are doing. That is equal to KE2 minus K. But what is this? U1 minus U2. Remember, WIC is minus of change in potential energy. So minus of U2 minus U, which is U1 minus U2. So what do you get here? Again, if you take it, U2 minus KE1 plus U1. You see, again you are getting into the work done by internal non-conservative forces results in change in mechanical energy. I said change in mechanical can be affected in two ways or three ways. Change in kinetic energy alone, change in potential energy alone, or change in both. It depends on the situation. So, when you have external work, you get delta MV. When you have internal non-conservative, then also it is equal to change in mechanical energy. Now I am taking internal conservative, external and internal non-conservative. Now you can very clearly see this is again from work energy theory, that is universal. If the system has all this, it is not isolated, non-conservative also present, then you have WE, WINC is equal to, I need not do that again, you are going to get change in mechanical energy. You get the point? Everywhere you can use pseudo force also, you will get this in the similar way. I hope this point is clear to you. Okay. All right. Right. Now you have looked at consequences of work energy theory. As I said, you can use it wherever you like, in any context, or you take all the forces into consideration. That is very important for you. Now, the other day I was talking about, we will look at now spring and gravity combination, how this work done, etc. will be affected. I am not getting into friction, only spring and gravity. Now look. You see, it's all light springs only, remember. If it is heavy spring, you have an issue. I will come to that. This is a light spring. Okay? Now, body, be careful of the language. Attached and released. This is the natural length. So what will happen to that? Suppose if I ask you, what is the maximum elongation in the spring? Maximum elongation in the spring. Suppose at this stage, I am saying, what is the velocity? Because you have just attached and left it. When it comes to one point, it can't go beyond, it will start its reverse motion, you know very well. What is the velocity at that instant? 0. What is initial kinetic energy? What is final kinetic energy? So, what are all the forces acting here? No viscous force, only gravity and spring force. So, work done by gravity and work done by spring force. You get the point? Work done by gravity and work done by spring force, that is equal to change in kinetic energy, which is 0. You got the point? Right. What is work done by gravity? Gravity force is acting downwards. Now let me say this is the maximum elongation. That's why I took velocity to be 0. Consequently, kinetic energy also to be 0. So when you take E max, force into displacement, that is constant. M, G, E max. I told you using this G in most of the cases, less than 100 kilometers displacement, close to the surface of a planet, you can take a constant G value, it doesn't matter. So this is a positive work. Now this is in the process of elongation. I told you, during the course of elongation or compression, work done by spring force is negative. So, minus of K E max square, and that is equal to 0. Now this you will get two solutions, isn't it? So one is E0, that is the initial state. Then the other one is what we have, E max is equal to, this is very, very important. Very, very important. Body attached. Is this body in equilibrium? No. Here is it in equilibrium? No. It's not in equilibrium. When is it in equilibrium? Equilibrium state, what is the equilibrium state? Mg is equal to Ke. Forces are balanced. Therefore, E is equal to mg by K. This is 2 mg by K. That means midpoint here. This is equilibrium state. You get my point? Now, you may be asked to find out what is the velocity as this body passes through this equilibrium position. How do you work out? Now, let me tell you. You have got Emax is 2 mg by K. Now, work done by gravity, work done by spring is initial kinetic energy 0. So, Ke, which is half mv square in equilibrium position. What is work done by gravity? What is equilibrium position elongation? We just found out. We'll substitute this later on. How do you write here? mge. Both are known positive. Process of elongation minus half Ke square is half mv square. Got it? Now, 2. So you bring everything onto one side. Ke square minus 2 mge. No, you can retain it like this. The purpose is different now. You want V. So, you substitute mg by K now. 2 mg into mg by K minus K into m square g square by K square. 1 K gets cancelled. Therefore, 2m square g square by K minus m square g square by K. So, this is mv square. 1m also gets cancelled. So, you have m by K You can verify it once again. E is mg by K, so I put mg by K here. So m square g square by K square. So I got, m also got cancelled. So V is equal to G times root of m by K. Okay? You can look at the dimensional compatibility also. This is force per unit length. So force is MA, M gets cancelled. So length by acceleration. Or if I go acceleration, root A into distance, so that is your V dimension. So no problem. So this is the velocity when it passes through equilibrium position. Initially you saw equilibrium position, you saw maximum elongation, you saw. You got the point? Okay. Can you tell me at this instant What is the acceleration of the body? Initial acceleration of the body. I have found out initial acceleration of the body. Simply go with your FBD. That is K max mg here. So how do you write? K max minus mg is equal to ma. What is E max? 2 mg by k minus mg is equal to ma. M gets cancelled. 2g minus a is equal to g. So that is a very interesting concept. You got the point there? Right. Okay. Likewise, they may ask at any stage, what is the acceleration in any given case? Is this clear to you now? They can also ask, if E is equal to mg by 2k, what is the velocity? You have to do the same thing. Initial position, take it as E. M minus half k square is equal to half v square. Substitute any E that is given. So you get the answer. This is when you attach a body and release it. Got the point? That's fine. What will happen to the body? It keeps on oscillating. Up and down, up and down. Now, I have attached a body and allowed it to come close, and then finally I remove my palm. This is mass, this is K. Now this is in equilibrium position. I made it to equilibrium at every stage. You get the point? What is the energy stored in the spring? Suppose I am asking you. See, this is an equilibrium. Equilibrium means upward force, downward force. They cancel each other. Therefore, E is equal to mg by k. Okay. So the energy stored is half k square. Potential energy stored in the spring. And the E, you may put it as mg by k. So you have m square. What is this? Potential energy of the spring. Likewise, you can get it. Okay? Now, you see, I am now bringing it by certain distance. I don't know, it could be, say, x, and then release, and then release. When it passes through this point, what is the velocity? Suppose if I ask you, then what do you do? One is work done. Okay? The other is energies. Here mechanical energy is concerned. Potential plus kinetic must be equal to 0. What is the energy in the spring at this stage? Half k. Another way I am telling you how to go about with energies. This is the one. Suppose it comes to this. It has gone up by how much? X. Okay? That means what has happened to the body's potential energy? Once it comes here, you get, see, initially I will take this as my zero level. Okay, I am taking that as zero level potential energy. And here what is the energy? I have only this much of energy. It goes up by X. So, potential energy, gravity has risen by mgx. At this instant, what is the potential energy of the spring? Half k square. But x is known here, and this is plus initial kinetic energy 0. So this is the kinetic energy at this stage. See here u0, here velocity v, my potential energy 0 here. Okay, so it goes up and then comes here. Or if you take this as 0 potential energy, this will be minus mg, whichever way you want you can do it. It makes no difference. Now you can find out what is your v from this equation. That is how you have to do it. Okay? Now when you look at this gravity, see generally what happens is, it's a very interesting case, remember. I will look at gravitational PE, body being risen, coming down, etc. is a well-known thing to all of you. Now I am going to tell you see, I am now looking at chains, ropes, strings, heavy. All of them have masses. This is a smooth surface, and this is the ground is on. You slightly pull and then release. The whole thing will come up. Okay? Now, see how am I attacking these problems? Now this involves purely gravitational. I am taking referential potential energy 0. Anything below negative, anything above positive. Is that clear? Right. Now what is the potential energy of the system? 0. What is the velocity here? 0. Now, by the time the last link leaves that edge of the table, what is the velocity of the chain? Now I am putting it here. Let us say the length of this is L, this is L. Okay? What is the potential energy of this? Of course it is negative, that is true. Okay? How do you get the potential energy of this? Now you take any distance x, you take dx. Let this be a very, very infinitesimally small quantity whose mass is dm. Therefore, the potential energy here is, of course, is below, therefore, negative minus dm g into x. Now, hereafter, be careful, this is a linear distribution of mass whose density, I will take it as lambda, mass per unit length. Mass per unit length is the linear density. Therefore, I write here minus lambda g x dx. Okay? Now, when I get the total potential energy, where x is varying from where? 0 to 0 minus lambda the x square by 2 0 to L minus lambda GL square by 2. But what is lambda in terms of mass? dm is equal to lambda dx. m is equal to lambda x 0 to L when lambda is constant. Valid if lambda is constant. So lambda L I can write it as in therefore minus mgl by 2. You got the point? Right. So what is the final potential energy? Now the final potential energy initially is 0, kinetic energy initial 0. This is minus mgl by 2 plus half mv because the entire chain has the same velocity. So what is V? Very interesting. V is equal to root GL. This is not a standard formula. Every time you have to work out, be very, very careful about this because no other force is involved. I could take it. Now in the same example, if lambda is equal to kx, lambda is kx, lambda is dm by dx, dm is equal to kx dx, 0 to L. This is the mass of the. You got this point? Now if it were to be lambda equal to k, previously lambda was constant, therefore V is equal to GL if lambda is constant. What is the velocity? Now same 0 plus 0 is equal to, now how do you get the potential energy? Minus dm g x and minus lambda g x. But what is lambda? Kx dx. So it becomes x square. Potential energy means 0 to x square dx is x cubed by 3. By substitute, so you get minus kg L cubed by 3 plus half mv square. I hope you are able to follow what I am doing here. I am taking potential energy when mass is uniformly distributed. I got that answer. If mass is not uniformly distributed, okay, then initial length has 0 density, that last one has got maximum density. In which case you will get, of course, m you can write it as kl square, but you bring this onto this side. Half m is kl square by 2 v square. Kl square gets cancelled. You get 4 by 3 gl under root. You see how much of difference 4 by 3 gl. What? In which case are you getting this? Lambda is kx. So depending on the function they give, you are supposed to work it out. Is this clear to you? Okay, now I think I'll put a stop to this here.